Okay, this is going to be a short video because one, I really got a bit excited in the last video and did most of this. And two, I really want to devote time for you to play with this, okay? Watching it's all well and good, but having you actually pull up the website, do it on your phone, do it on your laptop, whatever, and try to get a feel for what these slope fields are going to mean for what the solutions actually look like. But I want to start by asking you a question, okay? Specifically, I want you to think about, what do slope fields look like for specific kinds of ODEs? So what does a slope field look like, part A, for an autonomous ODE? Remember what autonomous means. Oh gosh, my N's and my M's. For autonomous ODEs. Okay, so think, what did autonomous ODE mean? That meant dy dt is some function only of y. Remember, usually they're a function of t and y, but it's autonomous if there's no t, if the derivative only reflects about y. Well, if we think about what slope fields are and what they look like, right, they're a bunch of slopes. Well, autonomous means the slope only depends on the y value, right? This is some function of the y value. It could be any function of the y value. But here the slope depended on y and t. So if you change the t value, the slope changes. If you change the y value, the slope changes. Here the slope only changes if you change the y value. So what do you think a slope field is going to look like for an autonomous ODE? Well, let me ask you a different question. Let's turn this into multiple choice. Which one of these do you think might be a slope field for an autonomous ODE? Do you think this could be the slope field for an autonomous ODE? The answer is no, right? Because the slope is changing with t. The slope must depend on t. But right here, I told you if it's an autonomous ODE, it shouldn't depend on t. It should only depend on y. The slope only depends on y. Okay. What about this one? Is this autonomous? This looks better. But notice it's a little backwards, right? As I change t, the slope changes. As I change y, it doesn't. So this is not actually autonomous. This is kind of like the reverse of autonomous, which we'll talk about soon. But not in this section so much. So it's not this one either. It's going to be kind of the flip side of that, right? Where this would be an example of a slope field of an autonomous differential equation, right? The slope depends on y, but it does not depend on t. The slope is constant across multiple t's. Okay? So that's going to be very important to think about. This one right here is autonomous. So if we give these different letters, right, our answer will be letter C. And specifically what that means is that for an autonomous ODE, once you have one solution, all solutions are just translations of that first solution. Every solution, you just move it up or down, up or down, left to right, and you get the same solutions. Let's go back to the mixing problem. Notice this was a slope field of an autonomous differential equation, right? The slope only depended on y. The slope did not change as you change t. All right? So once you get one type of solution, you can just move that solution to the right and you get another solution. Here's another type of solution down here. Move this solution to the right and you get that solution. So you can get infinitely many solutions by just doing a horizontal translation of another solution. Okay? So for autonomous, each solution can be horizontally translated to another solution. We'll use that later. Especially when we get to non-homogeneous solutions, we're gonna really be needing to get from one solution to another solution. And really that's kind of a fundamental part of any kind of differential equation, not just ordinary differential equations, but also partial differential equations, which again, we do not talk about PDEs in this class. They're more complicated. But yeah, being able to take one solution and generating another solution with it is really important. So that's one nice thing about autonomous ODEs. We can find infinitely many solutions just from one by translating it to the side. And similarly, what if we have a differential equation that looks like dy dt equals some function of t? We'll give you a name for this, but not quite yet. And again, this is going to be very similar. This is what this looks like. And again, if you have a function, an ODE, where the right-hand side only depends on t, you can get infinitely many solutions by vertically translating your solutions. Okay. So for the rest of the video, because I did talk a little bit more about that than I wanted, for the rest of the video, I really want you to go pull up this website. Let me change it so you can actually see what's going on. Pull up this website, Bluffton, their college's website for this professor, and play with this. Okay, what do you think these are going to look like? I'll give you an example, and then I really cannot stress enough how important it is. Go pull up this website, okay, right after the video. I'll make the video shorter so you have time. But yeah, and just pull this up and say, okay, what do I think is going to happen as I'm following these tangent lines? Is it a circle, a spiral? I'm going to guess a circle. All right, maybe it's an ellipse. I don't know. It might be getting stretched. It's either a circle or an ellipse. And in fact, they all look like that. Oh my gosh, that might be a little bug. I don't think that's real. I think that's a bug. But mostly it's pretty good. And you can read the about and this information. He does talk about some bugs that happen. Oh yeah, Daryl Nestor, thank you. Also, I found out to clear everything, go to initial points and you can clear. Then go to the ODE, choose another preset. And again, let's clear some of these extra ones and see if we know what it might look like. And again, you can kind of see this curve here that outlines this middle thing. And then you can also see if we're inside of one of these, we're going to be having some elliptical motion. And if we're outside of one of these, we're going to be having some kind of sinusoidal motion, like so. And again, when you immediately loaded it, that's when things were a little bit nicer on that one. The undamped pendulum. Yeah, you can really see, right? The different kinds of solutions here. Okay, so that's it for this video. We'll keep it shorter. Go play with this web page. Play for 5 minutes and then move on. All right, have a good one. Bye-bye.